Nice. That started so fast that we forgot to turn on the presentation and stuff like that, but we can do that too. Yes. Great. So welcome to our presentation. I'm the least important person here today. You have Jose as well. My name is Tobias. And we work for Boozt. And I'm going to do a slight introduction for Boozt, very, very short, with some slides and stuff like that. And then you're going to listen to Jose talk about payment gateways in databases, which is a very amazing story. To give you a short introduction to Boozt, we are now 1,200 employees. So we're 500 in Malmo, 600 in the warehouse in Ängelholm, and then 100 spread out in different development locations that we have. And then, so we are, you usually say we're the biggest e-commerce in Scandinavia, and then our biggest competitor is Zalando, so they have Europe, and then we take care of Scandinavia instead. And what we do is we sell fashion online, but now it's more than fashion. Now we also have home and sports and beauty and things like that. So we like to call it the Nordic department store now. All right, good, that's enough of that business talk. Then we also have another. What we like to say in the platform team is that we work with something called power to the people. So when we do work, we try to empower other people, so other business units or other developers or customers or things like that. So that's our motto is on the whole thing is that we create tools to other people, so we give power to other people to do their work. And then we have some questions. And I've been training on this to do the questions. So we have 5 questions, and I ask the question, and you raise the hand, and if you get it right, you get the prize. You get a nice t-shirt, so that's how it works. And it's also, you get some facts on the whole thing, so it's supposed to be fun and educational at the same time. Okay, good, I would do that. Oh, I almost pressed the first question. So the question number 1 is, how many developers do we have at Boozt? You're not allowed to answer. Anyone? Give or take? Closest is also... Yes. 700? That's one number. Someone wants to do... 50. Oh, that's also a good guess. We are 200 developers. So you were closest, whole thing. Yeah. So 200 developers. I got a question, why on earth do you need 200 developers to run a website? It's like Magento, you set it up and it's up and running. We do more things than just a website. We have our own warehouse management system, our own ERP and customer CRM tool and so on. So there's a lot of different systems that we work on. And one of them is the one you're going to listen to here, a payment gateway. Question number 2, how many locations do we have in terms of development locations? So we have different development centers. One is in here in Malmo, so it's more than one, at least more than 0, yes. Any guesses? Spot on, 5 locations. So we have Malmo, Aarhus, Denmark, Copenhagen, Denmark, and then Vilnius, Lithuania, and then Poznan in Poland as well. So it's all spread out. And we have Sima and Eister from the Vilnius office here as well. Cool. 3rd question, the number of systems that we made ourselves. How many systems have we made? 1 is the web shop. Any guesses? Yes? 3? That's a guess. Anything else? 100. Now I need to count. You're actually closer. We have around 40 systems that we have done ourselves. Yeah, we might have to divide the t-shirts here a little bit, but we'll figure that one out as well. But around 40 systems that we have ourselves, and they're not all. It's not like a microservices. I think it's a proper system that we have for our business. That's the answer. And this is a confusing. I still don't know how to ask this question, but I'll try it in some way. We have in our warehouse. We have an automation system that is supposedly the biggest in the world. Anyone knows the name of this system? I'm going to do a shout out to one of our partners. They should, yeah, you should get some kickbacks of this. I know you know. Yeah. Nope. But I might give you a yes. Yeah. Anyone else? We have the biggest auto store in the world. So it's a cube where it's running, and then robots on top of it picking. And so we have 1.2 million bins running in the warehouse. Or the bins are not running, the robots are running, and the bins are staying still, but they're running with the robots instead. So that's also something that we have. Yes, I'll stop with the question there, because the last one I can't even understand myself now, but that will, yes. Cool. So this is a little bit about Boozt. So we're more than just a web shop. We do different things. We have a big platform team. We're around 200 people working with it. And then one of those teams is the Boozt Pay team. And sometimes you meet people who are amazing. I have Jose here, and I have Axel and Rinal. And these people, they work on a payment gateway for Boozt. And Jose is going to talk about that from a tech point of view. So you don't need to hear my jokes or the corporate presentation. So Jose?
This now it's on, and I can hear now the echo, so I don't understand why the people in the video say that. All right, title of the talk. Every talk needs a title. An entire payment gateway in a database. And I want you to think, well, probably you already thought about the talk, had some expectations or not, but at least the title is intriguing, I hope. I want you to tell me what is the first question that comes to your mind when you see this title.
Why?
Oh my God, why? Exactly. Like, why? Why would you do that? So that's spot on. Thank you. You get a t-shirt. So this has two ways of being answered. So I'm going to give you the two answers. So the first answer is, why do we need a payment gateway, right? So to understand what a payment gateway is, we need to follow the money. That's what I see in YouTube in the conspiracy theories videos that I follow. So let's follow the money. When you pay at a store like Boozt, then you take your money to the store sends the request to a gateway, okay? The gateway doesn't deal with the money. It just tells a payment processor, please take the money. But the payment processor doesn't touch the money. It actually talks to an acquirer. The acquirer doesn't touch the money in most of the cases. Maybe indirectly, they talk to a card scheme like Visa or MasterCard. And then finally, it reaches your bank. So you can see it's a long journey. Then finally, your bank goes to, for example, Boozt's bank, deposits the money, and lets us know, like, yeah, the money's here, everything good. So you can see, like, it's a long journey. Usually the combination of these two here is called the PSP, Payment Service Provider. So you can be a gateway with the right of taking a credit card, like actually taking the number instead of a masked number or nothing. And what we're going to discuss today is just this part, gateway. That's what we have at Boozt. It's just a technical provider that is able to talk to a payment processor, like Swish, for example, and process a payment for you. So as you can see, a long chain of intermediaries. So the first problem that we encounter at Boozt is that the more intermediaries you have, the more problems you have. And this can be all sorts of problems like fees. We love fees. So here you have examples of fees that we usually get from payment providers. This would be from Ticketmaster especially. But as you can see, the more you have intermediaries, then the more you need to pay. So it would be nice if we could cut at least one middleman and cut at least the fee FIFO fee. And each provider, payment gateway that you sign a contract with is a contract that you need to negotiate, and it's a lot of discussions back and forth, and these are different pricing scheme. And that's a lot of work just to be able to pay. But since we're already doing that work, what if we can just do that work and benefit with better deals directly with the payment processors? And actually, you can strike better deals that way if you say, okay, this is our volume, we're a big store, let's negotiate another contract with us being the gateway instead of you. So that's pretty much the idea of why we wanted a new payment gateway. It's mostly financial reasons. If you think about a store as big as Boozt, payments is actually part of the core business. Like part of the thing that you do every single day is payments, reconciling payments, getting money into the bank, out of the bank, and so on. So it's part of the core. So when I got this idea for the project, I entered into a planning phase. Like, how would I do a payment gateway? So I represented the journey of a transaction from the point of view of a computer. So what we have is, this is like a timeline. And I need something that creates a payment request. Then to charge the customer with a payment processor, I update in the database or whatever. The status, I store some audit information. You always need audit. And then I need to notify systems via a webhook. That's as simple as I can get, right? But then, of course, you can see that things can happen. I have questions. How do I prevent duplicate payments? I can create many payment requests for the same order. And also, each of these steps could fail. I think you can see that, right? Creating a payment request can fail. Telling Swish to charge money can fail. Updating the status in the database can fail, and so on. So I need to, I think you understand the problem, right? Like, if I fail here, and I tell the customer, hey, something failed, like, you as a customer who's paying, you will get like really anxious about like, where's my money? Did you charge my card or not? So I wanted to prevent this. And then basically, I'm not sure why it's repeated this slide. So what the solution is that you need to think in terms of transactions. So there's a first transaction with the idea of an idempotency key. An idempotency key is a small string that identifies intention, and you can try with the same intention multiple times with the guarantee that if I try it 1,000,000 times, it will either fail 1,000,000 times or succeed 1,000,000 times, but in the backend it would just be executed once. So the first transaction is creating the idempotency key, send a request. The second transaction is larger. I charge the customer with a processor, update the database, store audit information, and the final transaction is notifying an external system. If you have any questions about what I'm saying, stop me, and I'm happy to answer. So the interesting thing about this is there is something weird about this. Like, if you think in terms of a database, like, you can easily think about transactions. But one of the steps here is not inside the database. It's outside. It's what I call the foreign state change. So I need to update another database that is not mine. So that actually is outside the scope of a transaction, which is quite annoying. And it's not just one. I have two here. So now I need to take care of systems that can fail outside of my domain of control. So these two things are not atomic. I can start a transaction in my database, but if it fails, then I'm pretty sure that my transaction won't do anything to protect me. Okay? So atomic means that I'm sure that a unit of work, once it's done, is persisted on the disk, and it's there. I can rely on it. But if things can fail in the middle, like, for example, I can charge a customer in Swish, but then I fail to talk to the database, what do? How do I recover from that? Okay, so those two are not really atomic. So I need to think in terms of how do I prevent that? I need to somehow recover. Like, if I fail here, I need to recover from here. If I fail here, I need to recover from here. So that introduces the idea of states, or like a state machine in a way. So you have, up until here, you have the state payment created. Up until here is called charge created. And then the last step is done. Okay, so as you can see in my two foreign state changes, it's not a coincidence that the arrows going up a line. Every time I have a foreign state mutation talking to an external system, I need to set a breakpoint. Like this is the point where I need to recover from if something fails. If I fail here, then I need to restart from here. If I fail here, I need to restart from here. Okay? So seeing those arrows going up was an insight for me. Like, what a coincidence. Like, it's convenient to have some arrows there. So I had two insights here. First is that the transaction flow is actually directed by the data. So it's about what I can see in my database is what determines what I need to do next. It's the data. It's not a request. It's not like instructions in the code that actually determines the flow. It's the data that I see in the database. Okay? And the second is, as you could see, I needed to create state changes for each arrow, for each mutation that was external. So the second insight is that I needed to minimize those. Why? Because it's quite annoying to have these breakpoints. It would be much easier if I could just have a script that runs until the end and I save in the database. That's it, job done. But if I need to make these breakpoints, I also need to have the work to restore from that place where I could fail. Are you following? Awesome. So this made me think that, well, that is kind of complex because talking to payments is, as you could see, a long chain of foreign state mutations. How do I keep complexity down? Like this kind of sounds like a complex problem if you think about it. So I'm going to take a very short detour to get us out of the tar pit. So out of the tar pit is a paper published in 1996, in 2006, which is extremely insightful, very long. I'm not going to make you read it. I'm going to give you a very short TLDR. But the purpose of the paper is how to tame complexity in growing systems. So this is the TLDR. It basically identifies three things. One is the main sources of complexity, what are the biggest offenders of each type, and the solution that is proposed. So there are three types of complexity. One is state, what I save, what I keep in memory, control, like each instruction in the code, and code volume, how much of those instructions do I have in the code. As you can imagine, the more code you have, the more difficult the project becomes. So for state, they identify that the biggest offender, the thing that makes the code the most difficult to understand and manage, is mutable state. Every time you can change state in memory, that's a problem. Okay? For control is having explicit concurrency. That is managing your own async, managing your own threads, managing your own orchestrator of jobs in the cloud. That makes the code more difficult to understand and manage. And for code volume, it's actually having too much power. Because if you have, let's say, a bunch of files that do nothing, then there's no complexity. But if each of those files can talk to any system in the world, write to the disk, call your mom, that's way too much power. So the solution for each one is, okay, for mutable state, we need to reduce, like as much as possible. Even ban it, says this paper. For control, we have explicit concurrency as the biggest offender. The solution is to ban it entirely. Do not have explicit concurrency. And for code volume is to restrict the power that you give developers when they code. So what are the specific recommendations? First is that data should be handled using relational algebra. Okay? You know what that is? So if you ever used SQL, that's relational algebra. It's a bit more advanced than just saying SQL, but let's simplify it to say SQL. To use a restricted language. So if I have a language that can do less, for example, a configuration file in YAML can do less than a Python script. So YAML is better for configuration because you're not making HTTP requests or doing crazy stuff. you know that whoever configures this is not going to mess up the system just by configuring. So let's use languages that restrict as much as possible. And one example would be a DSL, so a language that is specifically designed for the problem that you're doing. And 4 is that let another system handle concurrency for you. Just code in a way that concurrency is not an issue for you. So this, if you think about it, sounds exactly like a relational database. It uses relational algebra. It uses a restricted language, SQL. SQL is actually a DSL. It's a DSL for dealing with data. And it has one of the most advanced systems invented for handling concurrency. So the solution was kind of obvious, no? If I want to have a payment gateway that deals with complexity, it needs to live inside of a database. So how do we do that? Oh my God, keep doing this. So we need to have state in the database. So how do we do that? Quick refresher, remember this slide? This is our problem. We have the state here, we have foreign state there. So what we need to do is to notice that these things here are state machine. You know state machines? Yes? Okay. Because now we're going to talk a lot about state machines. So if we change this into state machine, basically what we need to do is break these transactions a bit more. And now add a few other states here. So I added initialize here. So this would be the first transaction. Then the second transaction is actually calling to the foreign state. So the only thing that can fail here is talking to the foreign state. I have another breakpoint here. And then whatever lives in my database can stay in the same transaction. So it can be quite long. And then again, talking to a foreign state is in its own state and transaction. Okay, so that's basically the philosophy of a state machine in the database. So the way you advance or move a state machine is by sending events. So you could call notify payment created, which would store a job. Then you notify change created at this point. Then notify payment done, which stores a notification job and calls the store back. And so here we call these transitions. We call these events. Okay. And then it's a problem of, okay, how do we represent state machines? Like, usually you do it like bespoke in some code. Like you have an array of here, goes to transitions there. But that's quite complex. Is there any way we can represent state machines in a visual way? So it turns out there is. This is another paper. This is from the 80s, in the 84. I was not born yet. But it was revised after I was born. That's a good sign. So it's called statecharts. It's a formalism. It's a way of drawing state machines in a way that is both a documentation and can be transformed to code. And that's just awesome. Whoever is a front-end engineer, this is actually a trend. You can check out this trend. There is a library called XState, which is how to handle state for React using state machines. So I'm going to give you a crash course on state charts. You have regions. So this is a region. This is another region. A region can contain subregions, can contain substates. Entering a state activates the substates inside. Actions cause transitions. So this is an action that causes a transition. And entering a state may call a trigger. So if you can go back here, you trigger this, then we call this action. That's a crash course. Questions? Okay, that's everything you need to know about state charts. So this is how you would draw them in a nice tool, but can we make this representable as code? Yes, actually there is a state chart, what do you call that, standard from W3C called SCXML. It looks like this. It's XML. In the 90s and 2000s, XML was the shit. And it's a really old thing, but it's amazing because there's even a VS Code plugin where you can write this and you get an entire system that you can just discuss with people that are not technical or semi-technical. And you can discuss, like, this is the flow of a payment, and then you can compile this to code. Isn't that amazing? So what we did is we adopted the SCXML standard, and we wrote a program that transforms this into SQL. So we basically wrote a state chart interpreter in SQL. So this is the input data. This is how you describe a state chart in SQL. We just write the XML. We see this. We're sure this is what we want. And then the program outputs this. And then we define, in this library, in this interpreter, we define an API for the state charts. So there's a function called create state machine with the latest state chart, with a version, right? So for the state chart named payment, create a new identifier that means this is a state machine. And then you can transition from one state to the other, sending events. You can start the state machine and then send events using notify. So to this state machine, send the event charge created with this data. So we tell, this is Postgres, by the way. So everything, all the slides are dealing with Postgres. So we created these functions that, by just calling this, it advances the state of a state chart in the database. If you have questions, obviously, stop me. Yes?
But isn't it a anti-pattern that a select would have?
This is a stupid question, so it's hopefully a very easy answer.
Yeah.
But isn't it that anti-pattern that a select would have side effects?
No, not necessarily. It's just a matter of what is available in SQL. Like the only way to call a function is by performing a select. So unfortunately, I would say it's a deficiency in the language, that the only way to call it is with select. It would be nice to say something like perform change. But yeah, good question. One thing is that we often call functions, I'm going to mutate something. So create, start, notify.
Yeah.
Okay. All right, so you could see that there was some sort of API for the state charts in the database. What if we could take this idea further? What if I could make an entire API for actually my API, what I expose to the world, inside the database? So actually you can. This is how it would work. So you have these write operations that should happen in the state machine. So you have the customer. The customer needs to talk to our gateway API. So this is our program in another language that is not SQL. But this program will execute this query. The query is executing the function create switch payment with some data that we got from the customer. And in the database, this function looks something like this. So create switch payment with some arguments. It starts or creates a new state machine. It inserts into the payments table. It starts a state machine. And that's it. The state machine will do everything. It will create the charge job. It will store in the payments table. It will do the audit, everything that it needs to do through the hooks that you saw that are triggered by transitions. So another example is once a customer pays, the payment processor, for example, Swish, calls our API, and then we execute in the database, confirm Swish payment with some data. And the function in the database looks like this. So find me the state machine for this payment, and then notify the state machine that the payment was done. How cool is that? All right, so we have covered state. We have covered how to restrict the developer to a DSL. Now let's talk about concurrency. So this is how you do asynchronous execution. So I'm not sure if you are familiar with something called the transactional outbox pattern. So in the world of microservices, this is the way of not fucking up. So when you have something that calls a foreign state mutation, but you also save stuff in the database, there's a problem. If something changes here and the request is retried, you will be doing the same thing over and over, maybe charging a customer many times. So I'm not sure if you have ever done a system, I'm guilty of this many times, where you in your whatever framework, you save to the database, next line, RabbitMQ notify this. You send a job to the queue. Or Redis queue, do that. So the problem is that you saved in the database and then you notified. What happens if the next line is crash? So you save something in the database, maybe it doesn't save anything because you realize I already did this job, but you save to the queue again. So now you have duplicate jobs, or jobs that are doing something that didn't persist in the database. This is a very classical problem in all distributed systems. So a pattern to fix this, called the outbox pattern, does this. So you have these two transactions that we have in the previous slide. This is our foreign state change. Remember, this is a job thing that we queue every time we enter this state. And then basically, the pattern is that you break the transactions so that at the end of this transaction, when we're sure the data was persisted on the disk and is safe, in that moment, as part of the transaction, before actually committing, is when you store the job. Okay? So the only way to do it is that by having a jobs table in the database. You store the job in the database, and then you have a program that is pulling those jobs out of the database that you know these are safe jobs to execute, and send them to a worker, maybe to RabbitMQ or directly to the worker. Did you follow this? Kind of? Okay. So it turns out that we don't need RabbitMQ. Postgres is a really fine queue. So we created an API for managing a queue in Postgres. So the API consists of these four functions: enqueue with some job as JSON, which whenever you enqueue, it triggers this notify. Then on workers, we listen on a channel. So they have a persistent connection to the database, and they get notified, like, hey, there's a new job, by notify. So this is the dual of notify. And then what does the worker do? They call dequeue. Give me any job that is pending. I'm not going to go into the details of this, but Postgres works extremely well for this. So this is how we queue jobs. Remember that we had a state chart, and I said that by transitioning to states, you can trigger actions. So this is how we represent actions. So when you enter the initializing state, on entry, we call the function enqueue payment create job, which looks like this. It's just a call to job queue.enqueue. So as you remember the transactional outbox that writes into the jobs table, and then there's a program pulling from the safe jobs that can be executed. Another example is when Swish notifies us, then we run these two triggers, notifying merchant of payment update, and another one. And this is the same implementation. As you can guess, it's just enqueue. How simple is that? So as you could see, we design an entire system visually. We just told it declaratively. This is basically the DSL, domain-specific language. And then we just have to implement very simple functions everywhere just to make the thing go. So this is how we do asynchronous jobs. But there's another aspect of concurrency, which is actually concurrency. So how do you deal with things happening at the same time? Like two payments from the same customer for the same order at the same time, a cancel payment at the same time that the payment is accepted. That kind of things are difficult to do. So I'm going to tell you a bit of a story. Back in the day, 2014, there was a news that a Bitcoin bank called Flexcoin had to shut down because someone had stolen all the Bitcoin they were holding. And then someone discovers that the problem was a race condition. It was a concurrency problem. And the concurrency problem was that they didn't understand how to use transactions in the database, basically. So they had two customers, and at the same time that they were making a payment, another transaction figured out how to withdraw from a payment that didn't exist yet in the system, that was not entirely persisted, and that's how they could drain all the Bitcoin from all the customers. Crazy, no? So transactions in Postgres have many levels of safety. Little safety, actually this is not a state, it's not possible in Postgres. Tons of safety, like this is the biggest possible. And these here are what they called serialization anomalies. So researchers have found that there are 4 types of anomalies, and then you can be susceptible to one of these, except for serializable. So I guess if you see this, you can put 2 and 2 and say, like, we should use serializable, especially if I'm dealing with money. So the serializable isolation level is a retry-based concurrency control system. Retry-based means that I send a request, and if the system can detect, like, this is not allowed because there's going to be a race condition, I throw an exception, and you have to retry as a client. So it's retry-based. It's not like it solves things magically. The only way to solve a conflict is to try again. And for those that have used Scala, Haskell, Clojure, is similar to software transactional memory. It's a way to magically solve all the problems just by retrying, which is quite cool because who wants, like, as a developer, I don't want to log a row. I don't want to think about how to concurrently solve problems. I just want to do my job. So if I can just put a magic flag, like, yeah, solve my problems for me, and carry on with my day, I would want to do that. Won't you? Yeah. So it requires no additional thoughts from the developer. So just use it. The problem, again, the caveat, is retry-based. You need to be prepared to retry. OK, that's it for concurrency. So let's talk about how uncool is to work with a database. Hackerman is a Swedish. So the first thing is that we treat the database as code, which is kind of revolutionary 10 years ago. So most teams today are treating database as code today. The way we do it is that we have one file per object, like table, trigger, index, thingy. We deploy changes to the database using CI. We just tell a program called Sketch to run our migrations. It adds columns, creates table, deletes columns, and so on. And in local development, we do the same thing. We run the same scripts locally. We run the changes, change the functions, verify they work. A typical workflow from my machine is I change something, it applies the things to the database. I made a mistake, now runs the test. Yeah, that database change is all right. It's actually quite cool. It turns out that you can also do testing directly in the database. There is a framework called pgtap, which we use sparingly. We have a combination of end-to-end tests and some smoke testing directly in the database. So you can write some queries, and you can use them as tests and verify that you haven't broken anything. For debugging, in the weird case that we don't know what a function is doing, we use pgadmin4. I have used it twice. It's not like a common thing for me. But for me, the biggest, most amazing thing is that you have a REPL. So you have a command line where you can try stuff. So you begin, try stuff. You see the results in tables, in changes in the system, and you can finally click run rollback, and your system goes back to normal, which is just amazing. You can actually do this in staging and production. Not recommended, because you have to remember to call rollback. So one observation of all of this is that our SQL code tends to be quite succinct. It's just a few lines of code, like maybe a big insert where you have a lot of columns, but we don't have a lot of ifs. We pretty much never has a for loop. It's very weird. And I would say that is the description of simple code. Code that you can just read linearly and say, like, this is what the code does. Do you want to know about the complexities of the entire system? You go to the state chart, and you can follow the step of what the system does. So we can also have static analysis. So we can statically analyze all of our queries, all of our SQL, and it will tell us you cannot deploy because you made a mistake. So in our editors, when we write the SQL, we get instant feedback that a query is malformed. But also, before deploying, we also get that a query is not compatible with whatever schema is in production. Yeah, and that's it. So finally, for observability and performance, I'm pretty sure many of you have heard, you who asked, like, why? Like, if you put a lot of things in the database is going to be your bottleneck. Have you heard that? Of course you have. So, of course, that was a concerning thing to me. Like, maybe it will be the bottleneck. So we built in a system to trace in the database. So for each query that we send to the database, at least a mutation query, we send two parameters in the memory. One called request ID, a UID that uniquely identifies a customer request, and some trace context from OpenTelemetry. So when we send this, this would be from our gateway. Someone is trying to capture a payment, and then it travels the database, it reaches the worker does some stuff, but thanks to the request ID and the OpenTelemetry stuff, we can know for sure that these two requests are linked. We can know that a web request corresponds to this job in the database. And actually, we can see retries, we can see future jobs, we can see scheduled jobs. Like, we can trace days of a request using this system. And we use Datadocs APM, which is quite cool tool, actually. We can see the performance of each query. Like, this is one of the most called queries in our system, which is in queuing a payload and queuing a job. And we can see, like, its performance over time. We can see it takes microseconds to execute, which is weird. They told me that the database would be a bottleneck. And we can see the top queries by time. So this M is milliseconds. We can see the slowest query we have takes 8 milliseconds in total. Yeah, and also we can see the query count per hour. So we can see if something is doing more work than it should. So an anecdote for performance. What you see here, these dates here are the dates of Black Friday last year. You can see that during Black Friday, there's a lot more queries. Caveat, we were just beginning with our system, so we just had one payment method. It's not like the entire Boozt. Still, it's Black Friday. It's more than what we used to handle. You can see what happens after Black Friday. Like, we have very little traffic in number of queries. So, do we have more t-shirts? Because it's another question. Yes? Like, can you guess how much CPU percentage in the master database we were consuming at the peak this day? Or can you guess how much difference from this to here? 10%. Someone else? 5%. So you win the prize because you were closer to 0. you can barely see. There's maybe like 0.5% of spike in CPU during Black Friday. Is the database going to be the bottleneck? Not anymore. I don't think so. All right. You may argue, okay, Jose, that was like very little traffic, just one payment. Like that's not representative. So after we pretty much started like ingesting the entire of Boozt as a payment gateway, you can see that the number of queries are 1 order of magnitude more than on Black Friday. Now daily basis, we get 1 order of magnitude more. Can you guess the CPU change? Yeah, you know the answer already. It's pretty much 0. You can see it's a bit more spiky because I activated the Datadog feature to query more stuff. That's Datadog basically. But you can see it's around 6% for 1 order of magnitude more queries. So I'm pretty sure, at least in terms of CPU, which is the main concern people tell you is going to blow up, that we can handle 1 order of magnitude more without going over 20% of database usage. And this is a really tiny database. It has 4 CPUs to handle the entire Boozt operation. So I think it was an inflammatory title. It's like an entire payment gateway in a database. I think like not really. Like if we count all of SQL plus PGSQL, it's only 21% of our code base. Of course, you need other languages to support this. Of course, you need another language to handle web requests and do other stuff, implement the worker. But 21% is decent. And basically, our core business, like the core thing that we do, lives inside that 21%. And that's the end. That's the end of my presentation. Do you have any questions? Thank you. Yeah, over to you.
Thank you for a great presentation. Well done.
Thanks.
Yeah. Any big learnings? Anything that you would have done differently if you started now?
Anything I would do differently? I think I would have invested a bit more time in the tooling for SQL because I think pretty much we were inventing it as we went along. Like if I could carry the knowledge of what I have today, I would say like invest in this type of tooling first and then do that, because at the beginning it was like difficult to figure out what the workflow should be. But right now we're super happy with the workflow for the most part. There are things to optimize. But yeah, I think investing a bit more in tooling would be my first thing to do. Yeah. Do you
Cool.
like we have 2 of the developers here, like would you do anything different? No. No? Not because I'm your boss. Yeah, no. We're happy.
You mentioned in the talk description, I think, that the decision was also based on sort of like the team's previous experience and what you were good at, what your strengths were. You
Yeah.
didn't really talk, like it was just in the description. So.
Yeah, okay. So I was doing something very similar in my previous job. Okay, what is my journey through life? I love databases. I have no idea why, but this is such an interesting topic to me. I'm the creator of twice an ORM for PHP. I used to be the lead developer of KPHP, and I did twice the ORM of that thing. I was super proud of it. And then I realized, like, wait, databases are capable of so much more. So I went into a route of, like, maybe the ORM, except for some use cases, like dynamic queries, are detrimental. So I started exploring that, and with great success at a previous company. Axel, for example, here, also tried to do that, less successfully, as I remember. But he already had experience. That's one of the big things I wanted him in. Like, I want to know your pain points and why you think this wouldn't work according to your experience. Because I was quite convinced it was doable. And like interestingly, the most of us didn't have a lot of experience with databases directly, so it was fun to have like clear minds. Some people that didn't know like this was possible, and teach them like, yes, it is possible, and see them enjoy it and see like, wow, this is quite cool. Was an interesting journey. But mostly the experience would be my life experience with databases for like more than 15 years. Anyone else? Don't be shy. Yeah.
Have you found any other uses for some of these ideas you've described? I assume that the idea of the state representation in the database, for instance, was something you did for this work. So have you used that for other stuff as well?
Well, this is the only project that we have used it, but one interesting thing is that it basically fits anything. Like the other day, like Axel was implementing a solution to fetch some data and transform into CSV, but it required multiple steps. So obviously this is a state chart. So like it's quite cool, like not knowing what Axel did. Like I was not paying too much attention to what he did, but I went and read the state chart, saw the image. It's like, oh, okay, this is what he implemented. It also infected the front end. We had a front end with React, TypeScript. Cannot remember what we used for state thing, but we got really upset with the state management in React. With hooks, with just hooks. And then we use state charts in JavaScript as well, and it's been amazing. Yeah, I haven't used it for a lot more things. I'm not sure if you, in your spare time, have. One piece of feedback that I got from someone, one of the developers, was like, wow, this is so cool. I want to use it for all the projects that I have. So like they could see that it was easily applicable to anything. But is that what you had in mind? Yeah. Well, I can tell you, like we're working only one big project, which is a payment gateway. It's the big hammer for every problem. Like everything fits into or must fit into a state chart because it's our ways of working. And when we have not used a state chart, like we have used like database triggers, which are quite easy to just use because they're just there, we have regretted it every time, and we made a state chart. Anyone else? Yeah, wow.
I'll do the insider question.
Wow.
We have, I already know the answer maybe, but we have Black Friday, the new Black Friday coming up. Do you have any like stress tests, or how do you see if this actually works going forward? I mean, considering the database, we don't think it's a bottleneck, but how do we know for sure?
Yeah, I imagine you want me to tell this funny story. Yeah.
Yes.
So last year, I went to Datadog, or the tool we use for insights, and I calculated how many transactions per second we received that day. So it showed it was like 30-something, 40-something. So I said, like, okay, if I can take the system to take 42 payments a second, that's it. I don't need to do anything else. So we took the time to do a stress test of inserting like crazy. It was quite interesting, and we were like improving performance, improving, until we saw, yeah, we can handle 50. So that's a bit more than Black Friday. We called it a day. We're ready for Black Friday. At that time, we were not handling the entire Boozt, so we were more than happy with that number. I said, like, for a year, we're going to be fine. And then this year, I reviewed the numbers again, and I realized I made a mistake. It's not 42 per second, it's per minute. So it turns out that I optimized the system for an order of magnitude more than what we need. So I think, I hope I'm not mistaken, that we're going to be fine for this Black Friday. Yeah, in retrospective, 42 a second was insane. Yeah.
So I've tried this once before, as you said, and there were some, it didn't work as smoothly as it did this time. And I think there were a few reasons for it. Like we had one enthusiast who sort of said, like, this is what we're going to do. And then for various reasons, he left. As we were left to like maintain this idea and didn't really know about things. And the one big thing, I think, is that we didn't know how the sketch tool works properly. So to like manage the files, like you want one file that describes a table and one function and so on. That became tricky if you didn't know the ins and outs of how to rework it, so you get a nice diff and so on. And also, I think we weren't using PLPG SQL as much as you should. You could, when you write SQL queries, there's also like an imperative version of it where you can actually have variables and more. And because some things are inherently imperative, and it becomes super messy to have this huge like query that's like with this, with this, with this.
Right. Yeah. That's true. Like I would say that the main insight here is know the tools that you use.
Yeah.
Like something that I do and people don't understand is that if I'm gonna use a new tool, like most of the times, I take an entire evening just to read the manual and know like, oh, this is possible. Oh, interesting. And then start like dreaming like I could use this feature for this. So if you get really intimate with the tools that you use, then it's a lot easier to not get stuck because you know what's possible in the tool and what's not possible. But yeah, I think that's the takeaway from this.
There's one other potential drawback, which is if you have a system, I mean, any system is fine with this. If you have a database and you change the columns or whatever, and then your code, and you can't deploy it in the same instance, there's going to be a slight mismatch where you have like the new database and the old code or whatever version you do it in. And when you have more of the stuff in the database, you'll also change you get this problem more often. Whereas if you only have dumb tables, you don't change the tables as often, and then you usually just add a column. So that's a problem that you need to maneuver around as well.
That's true. Like one of the problems that we saw in the paper out of a target is mutable state. So databases are mutable by definition. It's like the state of a system. At some point, you need some sort of mutability. So this is where you really need to take care of the system. Is like, how do I migrate from this state to this other state in a way that is compatible with the future code and the current code that is running. I think we have like sort of good tooling now for this. Like we have a tool that scans all the queries that we do and then tries to match it with the future schema that we're gonna deploy in the database. And it can tell you like, you're gonna break something, and it also does the opposite. Like we generate the future schema of the database and take all the queries that are currently running in production or possible to run in production and matches it with the future schema. And it tells you like, nope, the future schema will actually break production when you deploy it. Anyone else? We call it a day. Thank you. Pizza time.